Okay, so we will start our lecture. This lecture is about questions for preparation for midterm, and we will have two parts. The first part is signal analysis, and first question is shifting, flipping, and scaling of discrete time signals. So we may have our sample signal, something that maybe it can look like this. Let's make it -1, here +1, let's make it +2, let's make it -3. So this is our signal. So let's put the axis now. This is -3, this is -2, this is -1. Now here it is 1, here it is 2, here it is 0, here it is 1 in x-axis, here it is -1, here it is -2. The y-axis doesn't matter so much here, but anyway we may specify the values. So now the shifting property, shifting of this signal would be it can happen in two ways. So one way is x and let's say -1, and we will have the axis here, and when it is -1, it doesn't go to the left, it goes to the right. So by +1, so what was on 1, it goes on 2. So here we have 2, and we write here 1, here it goes to -1 because it's this. At 0 we get this 2, so at 0 we get this, and at -1 we get -3. This is -1, this is 0, this is 1, this is 2. This is an x-axis. So this is n, this is x, and -1. So because we don't really need to specify the y value, so I'm not writing them because it's mostly important in x. Now we can write x n plus 1. So again we need to draw the axis. Now it shifts to the left. So what was on 1, it is now on 0. it is on 0, this -1, then and this -3. So 0, -1, -2, -3. This is shifted to the left. When it says +1, it goes to the left. Shifting now. There is another one, flipping. So flipping is, we may write flipping here, because there is only one situation. So when we have this signal, when it is flipped, then it looks like this. We understand it as a reverse image. So what was on 1, now it is on -1. What was on 0 stays on 0. What was on -1 is now on 1. What was on -2 is now on 2. So this is the flipping situation. So shifting, flipping. Now we get to scaling. So scaling, there may be two situations. One situation is x n divided by 2. Another situation is x 2n. So the first situation, n divided by 2, although it's written that we need to divide, but we need to expand the signal. So we had our signal and now it looks like this. What was on 1, now it is on, we need to multiply by 2. So when we multiply by 2, what we get? What was on 1, now it is on 2. What was on 0, it is on, stays on 0. What was on -1, it goes on -2. What was on -2, it goes on -4. So this long -3 is on -4. So this is our signal. So this is -2, sorry, 2, 1, 0, -1, -2, -3, and -4. So this is how the signal looks like. It is expanded signal. Now this signal, this signal becomes shorter as we have this signal again, our first signal. So this signal we need to divide by 2. So when we divide 1 by 2, we get 0.5, so we get nothing. When we divide 0 by 2, we get 0, so we leave that y value on 0. Now we again, what is on -1, it should be minus 0.5, but we don't have values in discrete time with 0.5, 0.6 and similar. We have only integer values. And what is on -2, it is on -1. So our signal, it is like this. So this is 0, this is -1, and this is x2n. So we have answered this question. And the next question, question number 2. Question number 2. So this question number 2, it says, when we have signal xn and we do scaling operation, it is xn divided by, can be by 2, by 3, by 4, by anything, or x2n. So it's similar to previous one that we saw previously. But we can take a signal that can be more easily understood. So we may have here, we may have a signal like this. It's a good example. So we may have such a signal that it was in your book as an example signal in the introduction part, with discrete time, with example and the most common signals of discrete time. So this signal xn, this is n, this is xn. So what is the frequency of this signal? Period n. This signal, it is, we calculate the gaps 1, 2, 3, 4. So from repeating maximum value, we have n is 4, f is equal 1 divided by 4. So when we have n divided by 2, xn divided by 2, what do we get? So when n is divided by 2, we need to multiply by 2. So what was on 0 stays on 0. What was on 1, 7, 8, 9, 10, 11, 12. So what was on 0 stays on 0. What was on 1 goes on 2. So on 2 it is 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what was on 1 goes on 2. What was on 2 goes on 4. What was on 3 goes on 6. What was on 4 goes on 8. On 5 goes to 10. Now we can have 11. And here we may have 12. So this goes down here. So all these gaps are zeros. So we get some empty gaps. Again. All these gaps are zeros, and you can see if you calculate 1, 2, 3, 4, 5, 6, 7, 8. So now n is 8. So f is 1 divided by 8. So it means that here frequency is reduced as we have division here. Frequency is reduced. Now second option is when we have x2n. So now we divide by 2. So what stays on 0? So what was on 1, it disappears. So we have take 2 only, so it goes on 1, and all others are like this. So we take by division and we get f. This is 1 divided by 2 because n is 2. 2 gaps here. So 0, 1, 1, 2, 3, 4, 5, 6. This is n. So this is highest possible frequency in discrete time. So as we have multiplication here, the frequency increases. So this is the answer to the question number 2. Now we move to the question number 3. Question number 3, it is very simple question. Number 3, graphical representation of the delta function. So delta function is the basic signal that you can come up with, and it is at 0, it is 1. All other values are zeros. At 0 it is 1, at 1 it is 0, at 2 it is 0, at 3 at -1, at -2, at -3. So as you know the general theorem, then we move to question number 4. It is the discrete time signal expansion using delta functions. Delta functions. So this is question number 4. So any signal xn, discrete time signal, it can be expanded by a bunch of simple signals, delta functions. So this is the sum from k minus infinity to infinity, xk delta n minus k. So any signal can be expanded by delta functions that are shifted. So as you remember, in continuous time Fourier series, that was telling that any signal can be expanded by sines and cosines. Here it is something similar. So let's imagine that we have some kind of signal. Now we say we have graphical representation of the signal, and at 0 we have, let's have 1 at 0. I don't know if it's a very good example, but anyway, any example can be good here, I guess. Here is -1, here it is 2, here it is -1 again, here it can be -2, here we can have -3. So this is n, this is xn. So here it is 0, here it is 1, 2, 3, -1, -2. The values are, here it is 1, here it is 2, here it is -1, -2, here it is -3. Now y values are important. Okay, so this signal we can write as it is shifted delta function. Shifted delta function, and it is on -2, it is having 1. On -2 it is having 1, this value. So how can we make it -2? So we multiply all this all this graph, it means this value by minus 2. So we multiply by minus 2. This is multiplication. By minus 2. Now plus. At minus 1 we also have 1. We multiply by what? We multiply by minus 1. All this graph. Now plus what? Plus at 0. At 0 we have just a delta function. So we multiply by what? By nothing, by 1. At 1. At 1 we also will be having 1. And we multiply this by minus 1. Now we have another one. This is, we have at 2, we have also 1. And we multiply all this graph by 2. At 3, we have also 1. This is a 3. And we multiply it by minus 3. Multiplication by minus 3. And it comes up to the idea that it is what? It is the sum from what? From k minus 2 to 3. Minus 2, 3. N or k can be replaced. And it is the sum of xk delta n minus k. This is just a basic formula that we can write, but in general this sum we represent like this, and this is the main that I want you to know. That this signal is what? This is delta function shifted to the left by 2, so it means n plus 2 multiplied by minus 2, so here we have multiplication by minus 2. Now we add plus this. This is minus 1, multiplication by minus 1, and times delta function shifted to the left by 1, n plus 1. Now plus delta function itself, it is here, plus this one. So this one, it is minus 1 multiplied by delta function minus 1. Now we have plus this one. This is 2 delta function minus 2 plus 3 times delta function minus 3. So this is what I want you to know, how to expand the signal by delta functions. It is rather simple, and you can find it in the lecture that I learned these things long time ago, and they are explained quite well. We had this lecture in the class before our famous quarantine. So now we have question, what we have question 5. It is Fourier series. Now we come to Fourier series. Question number 5. Question number 5, it is, what signals are expanded by Fourier series? So Fourier series is used when we have signals that are periodic and continuous. Periodic and continuous signals. So when we have periodic and continuous signals, so it's basically, it's not made of samples, and in x-axis it is t. This would help you. And we have some kind of pulses here. Some kind of pulses. So this is signal, it is repeating at some kind of period, and you see that it is, this signal is expanded using Fourier series. Other examples that you may encounter somewhere, this is xt. So some kind of signal like this should be wiggling also. Some kind of like this you may get, because it's also periodic signal, it's repeating. This is t, this is 2t, this would be 3t. It is repeating signal. Now another kind of signal, it is you may get this kind of signal, just you need to recognize. So this is also, it is also periodic signal, continuous time signal. Another signal, periodic, can be similar to this one. We may have a signal like this, that it is repeating. So it is like this kind of signal, and if we were increasing this, it would be like this kind of signal. So it is repeating also. Or you can put period here, sign, in case what is repeating. So it reminds of anytime you have a repeating signal, so it means that you continuous time, it means that you are expanding using Fourier series. Now else 6. The first member of Fourier series, member number 1, has the frequency 100. Frequency, it is here omega. Angular frequency 100 radians per second. So as you remember, omega k, it was k omega 0. K omega 0. So now if we have omega 0, it is this guy. So the first omega, so omega, this is omega 1, sorry, this is omega 1. So now basically if sorry, this is omega 0. Now this is omega 0, so k omega 0. So omega 1 is 1 times omega 0, and it is what? It is 1 times 100 radians per second. So it is 100 radians per second. So basic trick here, there's actually no trick here, because if omega 1, if it is written that now I mixed you up. So this, let's write it is given that omega 1, it is 100 radians per second. It is given in the question number 6. So omega 1, it is 100 radians per second. So omega 1, it is obtained 1 times omega 0. So it means that omega 0 here, it is also 100 radians per second, as you may understand from this equation. So 1 times omega 0 is 100, and this is this. So 2, it is 2 times omega 0, and it is 200 radians per second. So as we go to 3, 4, 5, we get 5 times omega 0, and since omega 0 is equal to omega 1, so 5 times omega 0 is 500 radians per second. So basically there is no trick, just a multiplication, and just for you to how to determine what it is, that it's frequency multiplication in Fourier series. So I guess you know what you remember what Fourier series is, and if you don't know, you may find videos, or you may find examples on the internet, or you can go to our lecture. So now number 7 is what functions are expanded having signs by Fourier series having sines or cosines? So since sine is odd function, so odd functions are expanded by Fourier series. This cosine is even function, so even functions are expanded using cosines. And now to know from the graph, so very similar. I might have explained this in during the lecture. So this is, so even function, it is the one that is like mirror image of on y-axis. If you took the y-axis and minus and plus k and did like this, so then they would overlap. So it should be like mirror images according to the y-axis. So this signal is even. Now what is odd signal? Odd signal is, it looks like sine, so this would be an example of, this we don't need, this would be an example of odd signal. So this signal is even, this signal is odd. Now the third is if we have the signal that is this signal, but it's not a reflection according to y-axis, in respect to y-axis. So this signal is neither even nor odd. So even signals are expanded by cosines, odd signals by sines, and this by cosines plus sines. As you remember the lecture with A case and B case, so you can go back to this and watch that again. So now it is 8. What is the spectrum of Fourier series? So the spectrum, it is what? It is discrete and non-periodic. Discrete and non-periodic. Any time you see how to know if it is a signal or it is a spectrum. If it is omega here, then it is a spectrum. So here it is ck. Let's make it a magnitude of ck. And now you have a bunch of discrete values that may be random distributed or not. So you can make it like a mirror image, or anyway. This is 0, this is 1 omega 0, 2 omega 0, 3 omega 0, 4 omega 0, 5 omega 0. Minus 4 omega 0, minus 5 omega 0. So this is a spectrum of Fourier series. Discrete spectrum, non-periodic spectrum. Okay, 9. Question number 9. Question number 9. Discrete time Fourier series. DTFS. 9. What signals are expanded by DTFS? These signals are periodic but discrete time. Periodic and discrete time, so it means that it is the same signals as we saw previously. Where is that previous page? So these signals just represented in discrete time manner. So in discrete time manner, it would look like the first signal, it is like sampled signal. This it would look like something here, something here, something here, something here, something here, something here, down here, here. It should be repeating, so I might not get it like it should be, but it should be repeating signal. So this is the discrete representation of what I wanted to show about that signal. Other signals like this may also have their discrete counterparts, not counterparts, sorry, discrete representations. Now so we may now represent other signals that there were. So this is some kind of signal that reminds of as we had rectangular pulse. So this is like discrete representation of rectangular pulse. So it is even signal and it is expanded by cosines. what we need to know here, what is expanded is it's not as it is not asked by what it is expanded, so now another one signal may be like this. So this is some kind of representation of odd signal, and neither even nor odd signal would be like this signal just shifted. This is neither even nor odd. Now we go to question number 10. Question number 10 was, if the period n is 8, so how many different frequencies or unique signals are there in the TFS? So basically, as you remember, there was some from 0. There was some from 0 to n minus 1, and then there was this whole formula. So it means that there are how many members from 0 to 7, so it means that there are 8 different members. So there is no trig here. Again, 11. What is the spectrum of the TFS? So basically, if you see as a figure that looks like this, omega is here, and CK here. So the trick here is that we have periodic signal, we have periodic spectrum. So the spectrum is periodic, and we can see that this signal is repeating. 3 omega 0, 4 omega 0, 5, 6, minus 1, minus 2, minus 3, minus 4, minus 5. So if the discrete Fourier series has a period, let's say if the spectrum is discrete and it's periodic, what you need to know, it is discrete and periodic spectrum. So where the periodicity is here, it is here that you see the signal is starting here, and you may see that this is some kind of value here. Now two smaller values, one high value. Now it is again one high value. So this value comes to this big value. There is a small value comes to this big value. This is a small value and comes to this big value. So it starts from here. Should be this, and it should be like this. minus 6 omega 0, minus 7 omega 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, this is 6, this should be 7, this is somewhere 6, this should be 8, so 1, 2, 3, 4, 5, this should be somewhere 6, this is 7. So basically here as we begin from this, here I made a very complicated situation here. From this we can go to this. From this we go to this, so these values are repeating. So it means that we go to this, like this kind of signal. So this is 8 omega 0. I made a bit of complex situation here, but anyway you can see that this small value, that this is these are two small values. This is, we may call, not the highest value but the second in the highest values, so let's call it intermediate value, some kind of, and this intermediate value, then too small, then the highest, then intermediate, too small, the highest, then it is one intermediate again, and there should be something. Here it is intermediate value, too small, and one highest, and then it is repeating, and it goes from here also. So we have here we have 0, here we have this value repeating at 4, and we also have this value repeating at 8. Here we have this value repeating at -4, and here this value at -8. So this is kind of representation of discrete time signal, and this, the n here, it is 4, so it is n periodic spectrum. Maybe this is a bit complex situation. Maybe let's increase this value, so we will remove this. At least we will remove these dashes. So we need to increase this value. So now maybe, I don't know if it looks nicer, but it is correct. We have 1, 2, 3, 4 halves here, 1, 2, 3, 4 halves here, 1, 2, 3, 4 halves here, 1, 2, 3, 4 halves here. So maybe that was a nicer example in your lecture. This is a bit more difficult, but anyway, you need to know that this n periodic should be n periodic signal, and these are just repetitives of omega 0. So 12, what series I use to expand the signals? The signal is xt 5 cos 3 pi t plus I 5 sine 3 pi t. So it is given that it is dependent on t. It is t dependent, minus infinity to plus infinity. So it is periodic signal as it has cosines and sines, and it has t, so it means that it is fs. B, instead of t, there is n. So it means that here it is dtfs because it is n, so n is equal to integers plus minus. So understand here what's going on. It's easy. Now 13, you need to know how to determine from the graph what it is. So if you see discrete time signal n and xn, so if it's n, it's not a spectrum, it is a signal. So you see a signal like this, then it is repeating, and you see that it's periodic signal, discrete signal, so it is dtfs we use for it. If you see this kind of signal looking like it is t, this is xt, here it is something like this, here it is like this, continuous function, and then it is Fourier series. So like this. The respective version of continuous time to discrete time. Okay, now what we have else? This is what, number 13. Number 13, now we go to electronics. Electronical parts, so question number 14. Question number 14, so voltage, what is voltage? As I told you before, it is joules per coulomb or volts. The units are of voltage. So voltage, I will use two abbreviations for voltage. One is U and one it is V, and it is the same. U I use because not to double V in volts, but V we use with transistors. So U or V, it is the same for voltage. And voltage is joules for coulomb, so it's basically the potential energy that goes for 1 coulomb of charge. Potential energy, as you see, joules for coulomb. Joules energy for coulomb for 1 coulomb. And this energy, electric charge obtains this energy when it is positioned in electric field. When it is positioned in electric field, and this energy, we may call it potential energy, we can call it, that's right, energy is equal then to Q times U or Q times E times delta D. So this goes here. This charge moves in electric field. Okay, now what? Now resistance. This is like some kind of opposition for the moving charges. So it's measured in ohms, and for more deeper things you can review somewhere. You can review in the lecture, or you can review on the internet what the resistance is. So it is like specific resistance, and it is dependent on the length of the wire and the area of the wire. Now the current, and the longer the wire, the bigger the resistance, the wider the bigger the radius of the wire, so and area, so resistance decreases. Current is measured in amps, and it is coulombs per second. So it is the speed of flowing charges, of flowing charge carriers. So it is dq dt, so delta q delta dt, the amount of charge that has traveled to some kind of surface or length of interest through the wire during the time. delta t, and then you get the speed. Now Ohm's law. Ohm's law, it is what? It is current is equal to U divided by the resistance, the voltage divided by the resistance, and voltage drop, it is voltage U and it is current times the resistance. So when we need to know the voltage drop, we imagine you have small r and big R, two resistances, and you have voltage supply, and here, as the current is equal in all this circuit, you have I times small r and you have I times large R, and here you had U big and U capital and U small. So this, as the resistance is small, so it means that the voltage drop here it is small, and the resistance is big, that the voltage drop is big. Now power. Power is P U times I. The units are watts or joules per second, and as you know, voltage is joules per coulomb, current is coulombs per second, and these cancel out and you get joules per second, that are units of power. Other thing is work, it is, that's why it is A, power times time. Power times time, and it is measured in joules, and it is power joules per second or watts times seconds. And these cancel out and you get joules. So this is the work done by moving charge in the electric field. This one that was moving in the electric field by delta D, so this all potential energy was released as work. Now this was number 14. Now we get to number 15. Number 15. Symbols of electric circuits. Symbols. So voltage supply has the symbol of, this is minus, this is plus. This is voltage supply symbol. Capacitor. This is voltage supply. Capacitor is represented like this. We didn't have capacitor, but this accumulates charge. Resistor is like this. Diode was like this, plus minus here. Usually these signs are not written, but it is like this. Light bulb is like this. Transistors. Transistors, this is collector emitter, this is base inside, and this arrow goes outside. This is for NPN transistor. For PNP transistor, arrow goes in the opposite direction, and these are the symbols. Maybe not very nice, but you understand. So now number 16. Number 16. Volt ampere characteristics. So we did use during our lab works. So it is the dependence of current on voltage. So here it is voltage and here it is current. So this is the volt ampere characteristic. It's some kind of curve. So for light bulb the curve was like this, and this was plus 50, this was minus 50, this was what, plus 3, this was minus 3, and what was that volt ampere characteristics of the light bulb? So it was, so it is symmetric curve, and the light bulb has bidirectional conductivity, as we see current flowing here and current flowing here at minus voltage and at plus voltage. So bidirectional conductivity, and this is some kind of linear part, this is non-linear part, but in general, as the curve saturates, in general the curve is non-linear. Now number 17. This is some kind of exercise when you need to calculate. So P here is 40 watts. Power light bulb is connected to 220. So U is 220 volts. Determine the resistance of the light bulb. So you need to know the resistance. So here you know the Ohm's law, and you know that P is U times I, and you put this here and you get that P is U times U divided by R, and you get U squared R, and here you get that PR is U squared and R is U squared divided by P, and you get that it is 220 squared divided by 40. So you should get the result divided by 40, 1210 ohms. This should be the answer. Now 18. Number 18. Using which graduation of multimeter we can measure 0.05 amperes current at the highest accuracy. So here you will get a test question that it will be, as you remember, the multimeter had its graduation. So there was, like, it was here it was voltage, here it was resistance, here it was current, volts, resistance in ohms, and here it was current in amps, and there was like 200 microamps, like 200 milliamps, like, then what was, like, maybe 1 amp and 10 amps, something like this maybe it was. So you will get a test. So imagine that A answer is 1 amp, B 100 milliamps, C 20 milliamps, D 0.5 amps. So what it is here, what is the answer? So basically you need to know that this here it is 50 milliamps. So now let's go through these answers. This one is 500 milliamps. So which can measure? This can measure, but it is very high, big value. This is close value, it can measure. This value is too little, so this can't measure. This also can measure, but the closest to this one, it is 100. So this is the correct answer, because you can, with 20 milliamps graduation, you cannot measure 50. With 100 you can measure, with 1 you can measure, and with 500 you can measure, but this will measure with the highest precision. Now 19. Question number 19, it's given the power of the electric device, and it is given the voltage 220 volts, and you need to know the current. So the current, it is P divided by U, and it will be 200 by 220, and it will be 0.91 amps. So this value can be measured by what? It can be measured by, this is too low, too little, it can't measure. 910 milliamps it cannot measure, because this is higher than this. This cannot measure also, so this cannot measure, so we can measure only by this 1 amp. So this is close to 1 amp. 20. How are voltmeter and ampere meter connected to in electric circuits? So imagine, here it is resistance, here it is ampere meter, here it is voltage device. So ampere meter is connected in series. Voltmeter is connected in parallel. So why it is in parallel? You can think, or you can Google. I won't ask you this question, but you can find it yourselves. It depends on the resistances of the amp meter and voltmeter, and so it would not make discrepancies the current flowing. So number 21 now. What conductivity is common for pure semiconductors? So semiconductors, materials. So for this, so the answer would be that the values are the conductivity values of semiconductors are intermediate. Semiconductors are intermediate to maybe let's write between an intermediate to insulators, dielectrics, and conductors, so metals. And also the conductivity is bidirectional conductivity. Bidirectional conductivity. These two things you need to know. Now number 22. Number 22. primary and secondary charge carriers in P and N-type semiconductors. So P-type semiconductors. So primary charge carriers are holes. Secondary are electrons. So holes represented with P, electrons with E minus. So N-type semiconductors. N-type semiconductors. Primary electrons, secondary holes. Sorry, H, P. So imagine if you have an answers given C, D. So A is E minus, N 0, N plus, P plus, P minus, P, G, H. Imagine these have a lot of these possible answers, and the question is secondary charge carriers for N-type semiconductor. Secondary charge carriers for N-type semiconductor. So which are secondary charge carriers for N-type semiconductor? So for N-type semiconductor, secondary are holes, P. So you choose P here, because here it is written a lot of stuff like electrons, neutrons, N plus, this is something crazy. P plus, this is proton with plus sign, so this is not. This is proton with plus, this is proton with minus, something like crazy again. This is positron, this is N minus, something crazy again. So all these are crazy particles, normal particles or crazy particles, but the answer is P with no subscript, no sign. Okay. Now number 23. Number 23. Forward or reverse biasing of the PN junction. So this is plus, this is minus, and now if we connect like this, this is P, this is N, so this is forward biasing. This is forward biasing of the PN junction. And if you connect like this is plus, this is minus, this is N, this is P, this is reverse. Here the current is flowing, here the current is not flowing. Now 24, electric conductivity for a diode. So diode conductivity is unidirectional. Diode conductivity is unidirectional. Volt ampere characteristic of diode. So volt ampere characteristics of a diode was that you obtained during levels was U in volts, I in amperes, and it was like this. So what can we say that is asymmetrical compared to the light bulb? Asymmetrical, and it is unidirectional conductivity. This is asymmetrical. Conductivity is unidirectional, and similarity is that it also some kind of saturates as well. So these are differences, these are similarity. This is similarity, only one similarity. 26. Number 26. We go with final polarized transistors. 26. So common base configuration. NPN transistor, and we common base, so it was like this: emitter, base, collector. So this was R0, this was RL, this was load resistance, this is resistance at emitter, this is where the voltage supplies, this was VCC, this was called this was the voltage at the base or the emitter. So this was called in during our was called dB, and the amplification is K voltage. This common base we get voltage gain, only voltage gain, no current gain. So the voltage gain, it is as a ratio of RL divided by R0. So this is voltage gain. So as more different this, as RL is higher than R0, so then we get more increase in voltage. So now common emitter, we get NPN transistor, and we get what? We get, it goes from here to here, and it goes from here to here. So this is minus, this is plus, and this is VB. This is resistor RB, base resistor. This is base voltage. This is minus, this is plus. This is collector current voltage, collector voltage supply. This is load resistor, and this is emitter, base, collector. And beta was IC divided by IB. So this is the current gain. Current gain in common emitter. So we were dealing with current gains, but as we can measure voltages, the difference in resistances there is also. So we may multiply IC by RL, and we may multiply IB by RB. So there will be also voltage gain because RL is higher than RB, but it's we're more interested in current gain. So common emitter is used for both. This is used for voltage gain, and this is used for current gain and voltage gain, as it multiplies current. So now we need to go to number 27, transistor as an amplifier. So transistor as an amplifier. So we have covered all this topic in the previous lecture. So transistor as an amplifier and linear region of the transistor. So we can draw this volt ampere characteristics again. So these curves are, this is beginning with some, should be beginning with some nice curves, and then these curves, it's something like this. And here we have IB1, IB2, IB3, IB4. That's this will be equal to some kind of values. And here we will have IC1, here we have IC2, here we have IC3, here we have IC4. This will be IB5, this will be IB6, and this will be some kind of IC5, this will be IC6, and this is VCE, this is IC, and the highest possible voltage was equal to VCC, that was collector power supply voltage, and as you can remember, when transistor was used as an amplifier, this VCE was equal to 1 divided by 2 VCC. So this was half of collector power supply, and so this is when transistor was used as an amplifier, and you can see this region where these curves are evenly distributed. It is called the linear region. So this is called the linear region. So this VCE is selected to be in the linear region. So you can see here there are some discrepancies, and now this is called linear region, and from when IC is equal to 0, so and VCC and VC is the max, and it is VCC, so we mark an X here, and at VC equal to 0 and IC max, we mark an X here also, some kind of maximum value, and we draw a straight line, and where this straight line and according to this VC is equal to 1 divided by 2 VCC, we take the point in the straight line, and this point is called the quiescent point in the linear region, and it is used for, so Q point, so it is the operation point of the transistor, Q quiescent point, operation point of the transistor, and it is, we can describe this like VC is equal to half VCC, and here IB, let's write it 5 microamps, 10 microamps, 15, 20, So here it is IB3, it would be 15 microamps. And let's make it 1000. Here 2000, 3000, 4000, 5000, and here 6000. So at this point IC is 3000. So this would be microamps also, and this would be in volts. So this, let's make it as we had 3 volts during our laboratory work, so times 3 volts would be 1.5 volt. So this would be the some kind of representation of Q point, and at this, and B is 3000 divided by 15, it would be 200, since B is IC divided by IB. And what else? In linear region, in linear region, we have this relation. So it means that if we draw here IB, here IC, we have this linear, and B is tangent alpha. This is the angle. So here we have this question number 27. It describes the transistor as an amplifier. So as an amplifier, transistor is used. So here it is amplifier. So as an amplifier, transistor is used as VC equal half VCC. When it is amplified, it is in the linear region because this voltage is in the linear region. Voltage, the relation between IB and IC, they are proportional, and the relation is equal to beta, or we can write IC is beta times IB, and Q beta coefficient, this is the current gain, and the relation of IC and IB we get here, and Q point is described by all this. So all that question, it is here, and it is the answer is in this whole to all the parts of question 27. Now question 28. Question number 28. Transistor as a switch. So transistor as a switch, we need to go back to that figure that I'm not very able to draw very nice. So transistor as a switch, this looks like this, then this, and we see that here again it is IB1, IB2, IB3, IB4, and IB5. Here it is IC, and here it is VCE, here it is VCC, here it is 0, here are the values of collector current. So this is IC1, this is IC2, IC3, IC4, and so this is VCC. So basically these are two regions, saturation region and cutoff region. Saturation region and cutoff region. So in saturation region, transistor is like on switch. This is off switch, And here we get what? This is region, this region around 0, it is cutoff region. So this region, it is cutoff region. This region here, it should be this y-axis should be close to this, but I'm not very. So this would be saturation. This is saturation. Let's make it, this is cutoff. And what's left here, all this, it is linear region. So in saturation, what we have in saturation, we are close to 0. We should be close to 0 here. So it means that VCE is equal to 0. We should be closer here, but you can look at the somewhere on the internet a nicer picture. So VC should be close to 0. So it is close to 0. So this value should be closer, maybe somewhere here, but it's close to 0. And it is theoretical. But in practice, it is close. It is approximately 0, and during our lab work, it was around 40 millivolts. So it's close to 0. So this is called VCE saturation. VCE saturation. This 40 millivolts. Saturation voltage. In saturation, we have this saturation voltage that is close to 0. VC in saturation, we have VCE is equal to VC saturation. And VC saturation is close to 0, or in practice it is 40 millivolts. Okay, now what is IC? IC is equal to VCC, because as VC equal to 0, it's approximately equal to VCC, and it is IC max. Maximum collector current, because transistor is fully on. So here all the voltage drop is on load resistance, load resistor, and IC beta times AB, this relation is not valid. Why? Because if we draw like this, IB, IC, and we have this kind of graph, and at this point we get VC saturation. VC saturation at this point, because IB doesn't control IC. Base current no longer controls collector current. So this relation is not valid anymore. Because why? Because you can see IB is increasing, and here IC is no longer linear with IB, because this is high, this is some kind of gap, this is equal gap to this one, this is equal to this, and here these gaps come closer and closer, and they become all closer, and this what happens. So in cutoff region is very simple, and in this cutoff region, so here what also we have IB is higher than 0. IB is higher than 0. Here IB is 0, IC is 0, and VCE is equal to VCC. All the voltage drops on collector emitter junction. All the voltage from collector power supply drops on collector emitter junction. Okay, now all this you can find in the lecture more deeply with the circuit and with equations. And now the two exercises. So exercise number 29. So it is given collector current is 8 milliamperes, base voltage is 4 volts, voltage drop on base emitter junction is 90 millivolts, base resistance is 100 kilo ohms. So we need to know better. We need to know better, and for this we will use equations. IC is VCC minus VCE divided by RL. IB is VB minus VBE divided by RB, and IC is equal to beta times IB. So this is IC, this is IB, and this is equation that joins these two equations together. So we need to know beta. So IB is what? It is VB minus VBE divided by RB, and it is what? It is 4 volts minus 0.09 volts and 100,000 100, sorry, this is 20, this should be 120,000 ohms, and this is equal to 0.0000326 amps. Now beta is what? Is IC divided by AB. IC is given here 8 milliamps, and here there would be 0.0326 milliamps, and it would be 245 times. So current gain is 245 times. As you see, we used this formula and this formula, so this is quite easy. And number 30 is given. VCE is 45 millivolts, VCC is 10 volts, RL is 350 ohms, and IC is, we need to calculate. So we use this formula, this one, and we can easily calculate IC. It is VCC minus VCE divided by RL, and it is 10 volts minus 0.045 volts, and we divide by 350 ohms, and we get what? We get 0.028 amperes, and this is the answer. So basically this is it. Only the numbers will be given. The information for the exam, you can get maybe nicer graphs, nicer volt ampere characteristic, nicer circuits, nicer representation that I'm not very good at drawing here, but you can get in Word files that are in Moodle, in lab work files, Word files of lab works in Moodle. There is given a theory of transistors, of diodes, of light bulbs, and everything, and you can find also on the internet some kind of stuff on YouTube or anywhere else. And that will be it. So you have probably all the information for the exam, and if you have questions you can write me on email or somewhere, and I will write information on Moodle about the exam, and if you have questions just write me. Okay, so good luck.